Hopefully everyone had a happy Thanksgiving. Lots of food, lots of shopping, and rejuvenated to do some more MCAT studying. So today we're going to talk about electric circuits. So let's get started. Electric circuits. We defined, there's like 7 things we need to know about electric circuits before we start doing circuit analysis. The first thing we need to know about electric circuits is electric current. Current is generally defined as through the letter I. The units are charge divided by time. Q is the member of the elementary charge times some integer from last time when we talked electrostatics. The units for electric current is a coulomb per second, otherwise known as an ampere, denoted as capital A for short. Okay. So most of the time, it's usually some charge per unit time, right? How much coulombs do you have passing across some cross-sectional area per given unit time? That's your current. Current can also be, besides just written as charge over time, it can be written as the total number of electrons times the negative elementary charge divided by time. Capital N is the total number of electrons. Little n here is the molar amount of electrons times the cross-sectional area of the wire times the length of the wire times the negative elementary charge, all over time. And since electricity is always in some type of conductive material, they have what we call drift velocity. V subscript t is equal to some length over time, just the length of the rod, and divided by the time it takes for that electrons or charges to move. Okay. Lowercase t is time, capital T is period or tension, depending on what we're talking about. So lowercase t has always been time, right? Every time you guys did kinematics, it was always time. But capital T is period or tension. Sorry, we had a question asked, what's the difference between lowercase t and capital T? So we can rewrite current as the molar amount of electrons times the cross-sectional area times the negative elementary charge times drift velocity, V subscript D. And last but not least, we can also write it as what we call current density, which is simply current, which is usually denoted as some capital letter J. It's current divided by its cross-sectional area. So it's simply N, the molar amount of electrons times the negative elementary charge times drift velocity. So current can be represented as current density, can be represented as partially drift velocity in a conductive material, but most likely these are all the representations of current that you'll get. I've seen them all come into play. The most common one is charge divided by time, which is the original definition of current that I gave you guys. Okay, so all of these have come into play. And the units for all of this is always in some unit of ampere, coulombs per second. Okay. The next thing that we need to know about electric circuits is that the material used for electric circuits. materials with an S. So you always have some type of conductive material or some type of insulative material. So for conductors, we know that we have free charges. At equilibrium. And if you went to the electrostatics electromagnetism lecture, there's roughly around 10 to 23rd conduction electrons per cubic centimeter. Insulative materials do not have free charges. So we need to know how these materials relate to the term conductivity and resistivity. And then to do that, we need to introduce the third thing we need to know about electric circuits, resistance. So just keep in mind that any current carrying material has some resistance associated with it. There's some resistivity, there's some cross-sectional area that we care about, and then there's a length of that electric wire, right? Later, we're gonna put this in an electric circuit and we simulate it by calling it a resistor. But a resistor is actually any type of current carrying material that has a resistivity associated with it. Rho here is resistivity. The units for resistivity is an ohm meter, okay? So resistance R, capital R, is equal to the resistivity times the length over the cross-sectional area. The units are in what we call an ohm. The symbol is some letter omega, capital omega. This is the equation for resistance. So resistivity measures how resistive the material is to charge carrier flow. So in terms of a conductor, a perfect conductor will have zero resistivity. A perfect insulator will have infinite resistivity. The reciprocal to resistivity is called conductivity. That's 1 over. What's the term of the symbol for the numerator next to the length L? That's resistivity. The units are in ohm meters. Rho. That's how I write my rho. Some people write it as a P. Yes, resistivity is 0 when you have a perfect conductor. So the conductivity, it's an equal. The conductivity is simply the inverse of the resistivity. So 1 over the resistivity is your conductivity. The units are inverse ohm meters, okay? A perfect conductor would have infinite conductivity, and a perfect insulator would have 0 conductivity. Okay? So these are the units for resistance. And later when we talk about it in a circuit, we'll call it a resistor. Okay? But any current carrying material has resistivity associated with it, and with that resistivity, resistance based on the dimensions of the wire that you're carrying the current in. Any questions? So you need to know your resistance, need to know that conductivity is 1 over the resistivity that we have in our system. Any questions so far? Okay, shoot. The units of conductivity is inverse ohm meters, 1/ohm meters. Sigma is the symbol for conductivity, is equal to 1/rho, and ohm meters inverse. So 1/ohm meters. It's literally just divide the resistivity by 1. 1 divided by that. Okay. Fourth thing. Thanks, Monica. Ohm's law. Ohm's law simply states, given an electric circuit, the voltage that you have going across a resistive element, by the way, this is your battery on the left-hand side. It's a electromotive force. It has a sigma, or you can call it a voltage, right? Associated with it. The units for it are in a joules per coulomb, otherwise known as a volt. Denoted as capital V for short. And what it means is the charges that are coming out here, that just has a certain amount of energy per unit charge. So you have like a 1.5 volt battery or a 9 volt battery. There's just 9 coulombs or 9 joules of energy for every 1 coulomb that you have available. Okay. Current is going to go from the positive plate to the negative plate because we're dealing with physics, movement of positive charges. What Ohm's law states is the voltage that we lose across a resistive element is simply the current times that resistance, R. So V is equal to IR, okay, for Ohm's law. Any questions on that? EMF, sigma, or voltage? EMF, electromotive force. The fifth thing that we need to know about electric current or circuits. Some people write current as capital I. I do not, because moment of inertia is written as capital I. I don't know what they use for moment of inertia if they write capital I as current. But generally, I try not to write capital I because capital I to me is moment of inertia. So every time I see capital I assume a moment of inertia. Energy that's being given off in an electric circuit is usually supplied. It's just a variable. It doesn't really matter. Right? You go to publications and you see people writing like a bunch of Greek letters for all of this stuff anyway. But this is the universal variable that most books use, and that's why I tend to use it. Energy is usually supplied by the battery and dissipated by the resistor. The energy that we're talking about is the electric potential energy. The same energy we discussed in the electrostatics lecture. And that energy gives off heat and light. Little I. You understand that what I'm giving you is what the AMC gives you, right? Sorry, the question was, what does the AMC use for current? Six. The sixth thing that we need to know about work and energy. So when you think about how much energy is being used, it's not always measured in joules, right? It's always measured in some type of wattage. And that's power. Power is the rate of energy supplied generally equals the rate dissipated. Usually supplied by the battery, usually dissipated across the circuit elements, the resistors, the capacitors, the inductors. But for you guys, for the MCAT, you don't need to remember your inductors. So good for you. So power, we remember, is electric potential energy divided by time, right? And that's Q V all over T. So what's Q over T? Charge over time. We just went over it today. Current. Excellent. Good. Little I. Yay, a lot. So when we're looking at power, quick mnemonic to remember is when you need more power, reach for the IV. Okay? Now, knowing that and knowing Ohm's law, we can substitute in for V and we get I squared R. And we can substitute in for I and we get V squared over R. Both of these are saying the same thing, right? This is the amount of energy per unit time that we have being expended across the circuit. Joules per second. Units are still the same. It's still in the unit of a watt, okay? Where all of these is the equation for power, okay? Any questions so far? Okay. Let's give you guys a question. First question of the day. Potential energy is released as heat and light, Monica, right? Think of an incandescent light bulb. As we have electricity running across there, what do we see? We see light initially, and then over time, you feel the light bulb, it gets really warm and hot. So that potential energy or that electric potential energy that we have going across that circuit element is what's giving off light and the heat. So, first question. Given a circuit consisting of just a resistor and battery, if we double the length of the resistor, we then A, double the current flowing in the circuit, B, double the voltage output of the battery, C, double the power dissipated by the resistor, or D, have the power dissipated by the resistor. So we're given a circuit of just a battery and a resistor. If we double the length of the resistor, we then do which of the following? Double the current flowing in the circuit, double the voltage output of the battery, double the power dissipated by the resistor, or have the power dissipated by the resistor. Remember that a battery is created by what? The oxidation potential plus the reduction potential, going all the way back to our redox chemistry lecture in your electrochemical cells. So voltage of a battery is always dependent upon that oxidation potential and the reduction potential. Double the current flowing in the circuit, double the voltage output by the battery, double the power dissipated by the resistor, or have the power dissipated by the resistor. Okay, let's take a look. So we're doubling the length of the resistor. What happens to resistance? Remember, it was rho L over A. If we increase L, what happens to R? It increases. Good. So, and we know that voltage of a battery is what? It's always going to be constant. So voltage of a battery is equal to the oxidation potential plus the reduction potential when we did it way back when in electrochemistry, electrochemistry, and we talked about the oxidation potential and the reduction potential for a galvanic cell. So this is always constant in a system. So if we use Ohm's law, V is equal to IR, if resistance doubles, right, voltage is constant, what happens to current? Yes, it decreases. Good. So we know current decreases. So A is wrong because it doesn't double the current. It halves the current. We know voltage B is wrong because voltage stays constant. So now we're looking at power. Power is equal to I squared R or V squared over R. Okay? So if we just only look at R, this one we know increases. One equation says if R increases, then P should increase. And if R increases, the P should decrease. Which one's correct? So which out of these three terms, voltage, current, and resistance, is constant? The voltage, right? Good. So if voltage is constant, then this relationship is the most accurate in how it changes. The other one, you have to realize that current decreases, and since current is squared, it's going to decrease the overall power. So the best answer is it halves the power dissipated by the resistor. So if you have more resistance in an electric circuit, less current is flowing, less chance of you losing power or energy being dissipated across that resistor. So realize that like the amount of charges that are flowing is how you're transferring energy, right? So less charges flowing, less energy transfer or less power dissipation. Any questions on that? Good. Let's talk now about batteries. Seventh thing. So what's electric potential energy, Monica? Charge times voltage. Remember when we talked about it during the electrostatics lecture? Two weeks ago. Go back and have to look at your notes. Yeah, you can probably find it in the lecture notes. So, seventh thing that we need to talk about for electric circuits, and then we can finally do circuit analysis. And we need to talk about batteries. So with batteries, there's two alignments for batteries that you can have. You can have batteries in series and in parallel. So in series, the batteries are attached high to low, high, coming all the way out, coming back in, low. Low potential, high potential, low potential, high potential. Low is the negative, high is the positive. So for two batteries that are in series and hooked up, connected to each other, let's say this is a 6-volt battery and this is a 3-volt battery. Given that they have the same polarity and pointing in that same direction, you can combine them and get a battery that is a 9-volt battery. Okay. So batteries in series, as long as they're high to low, or the polarity is pointing in the same direction, are additive. Okay. If they're pointing in the opposite direction, they're subtractive from each other. Okay. Sure, I can draw it. So if we did the opposite polarity, so low to high to high to low, so plus plus. Yeah, so they changed the polarity of one of the batteries. So this is still a 6 volts and this is still a 3 volts. Collectively, they'd be subtractive, right? But the one that's pointing with the bigger voltage will end up winning, right? So think of it as like two different pressures of pushing electron gradients. So net effectively, it'll be 3 volts. 6 minus 3 gives us 3 volts, and it'll be going this way. But this is still both considered in series. Whether they're in the same polarity or opposite polarity to each other, where the batteries are opposing each other, right? You just either add if they're in the same polarity or as they go around in one loop, or you subtract if they're in opposite polarity to each other. Okay? So series, pretty straightforward. You just look at the polarity of the battery going from high to low, high to low. That's the way that the current wants to go, right? But if it goes from high to high and low to low, then it's going to be subtracted from each other, with the bigger one winning. That's batteries in series. By the way, all batteries, for all intents and purposes for your MCAT, are going to be direct current. Always DC. Direct current. Not to be confused with Batman or Superman. That's for Detective Comics. That DC is totally different. But this DC that you're always talking about with batteries is the direct current. That means current always flows from the high potential to the low potential for the battery. And when you have multiple batteries, then you look at the highest potential battery, and that's the one that's dictating current flow. Okay? For circuits in parallel, so the batteries are connected, and then they're connected to the rest of the circuit. So they are in parallel with each other. So parallel circuits, yeah, well, you can think of opposite polarity as being subtractive, right? So you can't say that they're all additive. I just gave you two examples where one's subtractive and one's additive.
I meant like because you said that they're all direct current. So does that mean that they're all the additive form of being in a series?
No.
Oh,
Direct
okay.
just means that the batteries, the current that's being pushed out, right? So imagine if you had this case, the 6-volt battery is going to push current out with a certain amount of force, right? And the 3-volt battery is going to push current out with a certain amount of force. And it's the difference between the two that gives you the overall current. Awesome. So with a parallel circuit, you're always going to have the 6-volt battery, or any type of batteries, they have to have the same voltage. So what a parallel circuit does is it gives you redundancy. So if you get rid of a certain part of that circuit, it will still function and drive current to the rest of the battery, right? So both of these are still going to be equivalent to a 6-volt battery. But what a parallel circuit means is that if you take that current out, the rest of the circuit doesn't die. So how you relate it to real life, like think of your lights that you buy at Christmas. If your lights are cheap, they're generally connected in series. And series requires less wiring because you can just put like one light after the other and just connect them with wires in between, right? And so if one light bulb dies, the whole chain of lights die. But if you buy the more expensive lights, they're connected in parallel. So when you lose one of the lights, the rest of the circuit doesn't die, and you can know which light is broken, right? So you probably experienced that already at some point, trying to do lights with your parents through Christmas and fixing them up. So things in parallel are just adding an extra layer of redundancy. So they'll still have the same overall voltage when two batteries are in series. Notice that in this case, the two batteries are connected to another part of the circuit, not just connected head to tail or high to low with each other, or low to high or low to low with each other. Okay, so just keep that in mind. Oh, depends. In a series, if you lose one light, right, in your series light for your Christmas lights, the whole chain of lights goes out, right? Because it breaks the circuit. But if you're in parallel, if you lose one light, the chain of the circuit still continues and you can have current still flowing to the rest of your circuit. So in parallel, only the light bulb that's broken goes out, not the whole string of lights. Does that make sense? For difference between parallel and in series? Series means that you're connecting one string or electric wire to the light and then connect it to the next light and so on and so forth. There's no additive nature because the two are just being replacing each other. So that's why I said if I took this out, there'll still be 6 volts, right? That's supplying to the battery or the circuit. If I took the other one out, I put this one back, and I took the other one out, it's still 6 volts supplying current to the circuit. That's why I said parallel cases is always an added layer of redundancy. Okay? Cool. So now that we know that, we can actually start doing circuit analysis. So now that we've gone over all the different steps from electric current, Ohm's law, conductors, resistors, resistivity, resistance, Ohm's law, and batteries, and the electric potential of batteries and power associated with it, we can look and apply Kirchhoff's rules. So whenever I get any electric circuit, I always use Kirchhoff's rules. First rule is called the loop rule. Simply states that the sum of electric potential difference in one loop must add up to 0. And we're going to apply Kirchhoff's loop rule in a little bit. And if you think about Kirchhoff's loop rule, it simply states that the sum of all the voltages as you go around in one loop must end up being equal to 0. And this is conservation of energy. The second Kirchhoff rule is called the junction rule. For the junction rule, simply states that the current going into a junction equals the current going out of a junction. Simply states that current in equals current out. And junction rule is just the shorthand way of saying conservation of charge. The same amount of charge that we have going in equals the amount of charge that we have going out. So let's take a look at Kirchhoff's loop rule by looking at things in series, okay? So 2 rules about things in series. So let's look at things in series. The first rule is that the current flows through only one path and it stays the same. However, the voltage difference of each circuit element can be different. So let's take a look at Kirchhoff's loop rule in action with a bunch of resistors in series. So this is some voltage from a battery. This is, we'll call R1, R2, R3. Plus negative, plus negative, plus negative, okay? So we know current goes out from the high potential or positive plate all the way to the negative plate. So V minus I R1 minus I R2 minus I R3 is equal to 0. Notice it's the same I because current stays the same in one loop. There's only one path for charges to flow. So therefore the charges stay the same. They don't become different currents flowing in different paths. And we know that we lose voltage across every circuit element across resistor due to Ohm's law, because remember we consider that a voltage drop, IR, okay? Now if we separate it, we can get this into I times R1 plus R2 plus R3. If we simplify this into a circuit of just that battery and what we call an equivalent resistance, REQ, you guys call it R total in the book, we can write it as I, REQ is equal to I times R1 plus R2 plus R3. And by using Ohm's law, we can get rid of the current because we know the current stays the same. By using Ohm's law, we can see that resistors in series are additive. REQ is equal to R1 plus R2 plus R3 plus how many other ... resistors that we have in series with each other. Okay? So this is how I use Kirchhoff's rule to see and derive any type of circuit element interaction that I have. And I love Kirchhoff's rules because it works anytime. I use this when I do from complicated electrical engineering, from circuit design and circuit for my PE tests and stuff like that. And for any professional engineers that I'm working with and doing their circuit design, I just use Kirchhoff's rules. And I look at each of the loops depending on how complicated the circuit is and do that circuit analysis. And if you think about it, it's just a system of linear equations, right? The more loops you have, the more equations you have. And so you just take that system of linear equations and eventually you can find out all the currents running through your system. Okay. The number of unknowns equal the number of equations you have. It's a solvable system of linear equations. Okay. For the MCAT, you're just going to deal with one equation. You're not going to deal with multiple. Trust me. Okay. All right. So now let's deal with things that are in parallel and take a look at junction rule. Okay. So for things that are in parallel, there are two rules as well. The first one, there is more than one path for current flow, right? There's multiple paths, in fact. However, the voltage difference between the different paths stay the same. So let's take a look at how those voltage difference between the different paths stay the same. And now we're going to look at things in parallel and how to do circuit analysis for this. Let's say we have multiple resistors in parallel. Call this R1, R2. Here's the voltage from our battery. So we know that current is going into a junction. So this is a junction. We'll call that I, and it splits into I1 and I2, respectively. So Kirchhoff's junction rule simply states current going into a junction, the total current, is equal to the current coming out, I1, plus I2. So I can be rewritten as the voltage divided by the resistance, plus the voltage divided by the resistance. I'm going to draw in red what I consider high voltage or the same voltage. I'm going to circle it. So this is all high voltage, right? And I'm going to draw in blue what I consider low voltage. It's like cool. It's not hot. This is all the same voltage. And if you notice, going from here to here, that's the same voltage drop. Going from here to here, that's the same voltage drop. That's how I can write the same V for both of these. V over R1 plus V over R2 for I1 and I2 respectively. Now, if we simplify this down into a one battery, one resistor circuit, and call this the equivalent resistance, that I that we're going to deal with is what we call I total. It's going to be the total voltage divided by the total resistance. Voltage divided by R1 plus the voltage divided by R2 for the other side. We can cancel out the same, since they're all the same voltage. Voltage difference is the same for parallel circuits. And we saw that earlier with the batteries as well. We can cancel out all those voltages, and resistors in parallel have this 1 over relationship. 1 over Req is equal to 1 over R1 plus 1 over R2 plus ... How many other resistors we have in parallel with each other. Okay. If we want, we can rewrite it for two resistors. Req is equal to R1, R2 all over R1 plus R2. For three resistors, we can rewrite it as Req is equal to R1, R2, R3 all over R1, R2 plus R2, R3 plus R1 R3. In each case, what am I doing? Finding the common denominator, adding them up, and then taking the reciprocal from this equation. Okay? So you can choose to remember each of these individual ones, or you can just do fraction math. Okay? So this is how I analyze for resistors in parallel using Kirchhoff's junction rule. That current splits. So the current that we have coming in equals the current that we have coming out from that junction. Okay. All right. Any questions so far? All right. Let's give you guys your second question. It's a multi-parter. Okay, no worries. It's a lot. It's a lot to get in. There's a question. If you have 3 resistors in parallel, can you use the shortcut in the first 2 and then do the same trick for the third? Or you can just use the shortcut I gave you for 3 resistors right here. So you don't have to worry about it. This is meant to be an arrow. I just use this equation. Sometimes it's just easier to do though, if they're all the same resistors, like 1/2 or 1/3, 1/3, 1/3, and take the reciprocal, that's just 3 over 3. And your equivalent resistance would have been, right? If you have 3 ohm resistors in a row in parallel, then they are equivalent to 1 ohm resistor. Yeah, you just have to do it again for the second one. You can do 2, and then you do the same thing with the equivalent one for the first 2 and the third one. It just seems extra tedious. Especially since there's an equation there for you. Good. Yes. I generally don't commit it to memory, but I mean, some people like to, and that's why I put it out there. I like doing the process, right? Because understanding the process means I can apply it to any varying situation that they throw at me on the MCAT. So by understanding Kirchhoff's loop rule and junction rule, they can give me any complicated circuit that they want in biochemistry, right? As long as I see a resistor, a battery, a capacitor, I can analyze the bejesus out of it, right? And find you anything you want. Okay, second question of the day. We have a battery, which then splits into 3 resistors. Okay, so the voltage I'm given here is a 12-volt battery. That's equivalent to what you have in your car. We'll call this R1, R2, R3, R4, respectively. And I'm told that R1 is equal to R2, which is equal to R3, which is equal to R4, which is equal to 2 ohms. Okay. I want to know, what is the total current coming from the battery? B, what is the voltage across R4? C, what is the voltage across R1? D, what is the current across R2? E, I want to know what the power is across R3. So all those things that we talked about for the first 7 things that we need to know for an electric circuit, please apply them now. I total is the current coming out of the battery. Remember, junction rule and loop rule still apply, right? Conservation of energy and conservation of charge still apply. All the resistances are the same. Figure out what's in parallel, what's in series, and then go from there. You guys a total of like 5 minutes. 2 minutes have passed already. 3 more minutes. I1 is the current across R1. I2 is the current across R2. And I3 is the current across R3, respectively. Okay. What'd you guys get for the total current? Got 9 amps, 6 amps, 4.5 amps, 8 amps, 3 amps. I think that's a good enough for A, B, C, D, E. Yes, anonymous. Voltage across R4. Given those amperages, should be 18 volts, 12 volts, 9 volts, 16 volts, and 6 volts, respectively. Voltage across R1. Given those voltages, should be negative 9 volts, 0 volts, 3 volts, negative 4 volts, and 6 volts, respectively. Current across there. Those voltages divided by 2, negative 4.5 amps, 0 amps, 1.5 amps, negative 2 amps, and 3 amps. And the power associated with it, it's just the current times the voltage. So it's 9 times 4.5. 9 is 36. Half of 9 is 4.5. So 40.5 watts, 0 watts, 4.5 watts, 8 watts, and then 18 watts, respectively. Okay, so let's take a look at how we got this. I'm just giving it based off your total current that you found. So how do we find total current? That's the key. We need to find equivalent resistance, or REQ. So what resistors are in parallel? What resistors are in series? What's in parallel first? Okay, Jonathan is correct. R1, R2, R3 are in parallel. So 1 over 1 through 3 is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So find that and then sum it to R4. So this should be what? 1/2 plus 1/2 plus 1/2. That's 3 halves. So R1 through 3 is 2/3. Right? And then we're going to add that to R4 because they're in series, which is equal to 2. Did you forget to take the reciprocal? It is. It is that easy. So this is R total, right? REQ. It's okay. Everyone makes mistakes. That's why we're here to learn. So REQ is simply the sum of the R1 through 3, which we got as 2/3 of an ohm. And you add it to R4, which we know is 2 ohms. So 2 and 2/3, or 8/3 of an ohm, to make it an improper fraction. Right? 2 and 2/3. So how do we find I total? I total is equal to V total divided by REQ. So that's 12 divided by 8/3, or 36 divided by 8, That goes into it 4 times, and 4/8 are left over. So 4.5 amps. This would have been your answer choice A, answer choice B, C, D, and E, respectively, right? For your MCAT, each column. So we see that we're 4.5. Look at that. I'm inclined to choose C. Let's look at the other case. Voltage across R4. So I comes in. Isn't this still I total? Right? So this was A. B was simply VR4 is simply I total times R4, which is 4.5 times 2, which is 9 volts. I total is 4.5. R4 is 2. It's 9 volts. Look at that. So far, this column's looking pretty good. R1. So if we know that to go from here, this is cool, to here was 9 volts, and this started as 12. 12 minus what equals 9? 3. Because blue is 0 volts, right? And red was 12 volts. So it had to be equal to 3. Voltage of R1 is equal to 3 volts. Because it's dropping 12 to 3. 12 minus 9 is 3 across each one of these. 3 volts. I2. If we know that VR2 is equal to 3 volts, then I2, R2, and R2 is what? 2 amps? Or 2 ohms? Then I2 is equal to 1.5 amps. And last but not least, the power across R3. We know I3 and we know VR3. I3 is 1.5. And the voltage is 3 volts. So that's 4.5 watts. So each of these answers. Looks like answer choice C is the most correct. There's the answer for part A, B, C, D, and E, respectively. Looking at the voltages and the currents using our junction rule and our loop rules. Any questions on how we got that? Sure. How did I get C? So notice the thing I drew in red, Michaela? All of that's high voltage, right? That's 12 volts for a 12-volt battery. And blue was 0 volts. And from B, I know that I dropped 9 volts across this section right here. Right? So going from that green to the blue, I lost 9 volts. So this green had to be 9 volts to drop to 0. So 12 minus 9 is 3. Cool? That means it's the same for 12 minus 9 for R2, for R3. That's the voltage drop across them. And it makes sense, right? Because everything that we see in parallel has the same voltage drop. Does that make sense? Any other questions? Cool. Everything else makes sense for VR2 and the power dissipated across that resistor? Sure. What's I2? I2 we know is what we're trying to find. We know VR2. VR2 is 12 minus 9 is 3. We know R2 is 2 ohms. So what's 3? 3 is equal to I2 times 2. 3 divided by 2 is 1.5. Cool. What about everyone got E? We're good there. Any questions? All right. Let's move on. Let's now talk about your capacitors along with your resistors. Capacitors. So the job of a capacitor is to separate and store charge. So here's your battery. Capacitors in an electric circuit are just those parallel plates that we discussed way back when we did electrostatics, electromagnetism. Okay. Here's your voltage from your battery. Here's your C, or what we call capacitance. So capacitance is a measure of the physical property of those two parallel plates that we talked about. We have the permittivity constant of free space, epsilon naught, times the surface area of the plate divided by the distance between the plates, d. Where epsilon naught is 1 over 4 pi k. That electric constant, 8.99 times 10 to the 9th. I also gave you the permittivity constant when we went over it way back 2 weeks ago during electrostatics lecture. Okay? So that's the equation for capacitance. It's a physical property of those parallel plates. So the charge associated on these parallel plates is simply the voltage that we can have, the maximum voltage we can place across there, times the capacitance that we have for those plates. So Q is equal to voltage times capacitance. Another way to remember that, if you're insomniac, right? QVC, that's how I remember it. By the way, the units for capacitance is called a farad, denoted as capital F for short. Farad after Michael Faraday. Okay. He of the famous Faraday's law and your Faraday cage, all those like physics things that you guys discussed way back when. Also the guy that did the combustion analysis too for whale oil way back then. So let's take a look at what happens when we have a capacitor with the dielectric. So capacitors So before, when we put a dielectric between there, we know that it reduced the overall electric field, right? But now that we're attached to a battery, can't really do that anymore. The voltage is the same. So with voltage being the same, we know that we have charge buildup on these plates. That's going to create charge separation within our dielectric. Right? It induces an E field that opposes the external field that we have. Right? But D is still the same. Voltage is now constant because of the battery that it's attached to. Voltage doesn't change with the electric field. Remember the equation V is equal to E D? Everything is constant. So voltage is now constant. D is constant. That means E can't be reduced. So E has to try to remain constant. How does it remain constant in an electric circuit? It continually, since E got reduced, added more charges. To the plate. And in doing so, it creates more charge separation between the dielectric material. And this process continually happens. So when we talk about having a dielectric between your parallel plates, it increases the amount of charge you can hold, separate, and store, right? Hold, separate, and store. Up to a certain point, and that certain point is what we call dielectric breakdown. That's when your charges that you've built up on the plate have become so great, they literally rip the dielectric material apart, ripping the electrons from the protons for those atoms in the dielectric substrate. And you hear it all the time in EE lab or E&M lab. As a TA, you hear this little pop sound. That's when the capacitor is broken and your dielectric is ripped and you've left the battery on too long for that capacitor, for that the capacitor to store charge. It added too many charges and it popped your capacitor, which means the capacitor isn't separating and storing charge anymore. It's just behaving like a straight wire. So just be careful when you guys do your lab for E&M, when you're doing circuits, when you put it in, this is what happens. But before that, the capacitors with the dielectric, simply that dielectric constant times your initial capacitance in your system. So it's really just that dielectric constant times epsilon naught times A, or the cross-sectional area, divided by the distance between the plates. So as we add a dielectric, we increase the capacitance or the ability of the capacitor to store and separate charge. Okay. Let's take a look at capacitors in series and then capacitors in parallel, and then we'll look at RC circuits. With things in series, we're still using Kirchhoff's junction rule. We'll call the C1, we'll call the C2. So here's the voltage. So the voltage as we go around in one loop is equal to the voltage across capacitor 1 plus the voltage across capacitor 2. And the voltage is simply the charge over C1 plus the charge over C2. And remember, for things in series, there's only one path for current to flow or only one path for charge to flow, because current is the amount of charges per given unit time. We can rewrite this as a single battery, single capacitor. We'll call that equivalent capacitance in a circuit. There's your voltage. Will be charge all over CEQ, or the equivalent capacitance. So that's why the capacitors in series, you can cancel out the charge because there's only one path and the charge stays the same. It's not really 2, it's just Q. 1 over CEQ is equal to 1 over C1 plus 1 over C2 plus ... how many ever capacitors you have in series. So capacitors in series look very much like resistors in parallel, have that 1 over relationship. You can use find the common denominator, add them up, and then take the reciprocal method. But that's literally all you're doing when you're doing this type of math for capacitors in series. The other case, capacitors in parallel, we're going to use junction rule. For junction rule, these are all in parallel with each other. We'll call this C1, we'll call this C2 respectively. And all it's saying is that the junction rule that we're applying, this is the junction. The charge total is equal to Q1 on capacitor plate 1 plus charge 2 on capacitor plate 2. And Q is equal to VC, right? So it's the voltage times capacitance 1 plus the voltage times capacitance 2. And we know things in parallel have the same voltage, so we can just simply write it as the same V. Now, if we make this circuit into a one battery, one capacitor circuit, or what we call the equivalent circuit, there's your battery, there's your capacitance. We can write that as battery times the equivalent capacitance is equal to the total charge going across both of these capacitances. And since for things in parallel, voltage is the same, we can cancel it out and we can see that CEQ is equal to C1 plus C2 in your system. So capacitors in parallel are additive, just like resistors in series, okay? So just relating back using Kirchhoff's loop rule and junction rule in our system. All right, so now let's take a look at an RC circuit. An RC circuit has both a resistive element, circuit has both a resistive element and a capacitive element in the circuit. So let's draw it out. Here's your battery. Here's the switch. Here's the current. Here's the resistive capacitive element. We'll call this generic R. We'll draw this generic C. Okay. Here's your voltage from the battery. So at t is equal to 0, that switch is closed. So let's take a look at what happens at t is equal to 0. At that instantaneous point in time, all the current is going through the resistive element. I is equal to the voltage from the battery divided by the resistor, because the voltage of the resistor is equal to the voltage of the battery. The reason being, capacitors have what we call electric flux, and initially it has 0 electric flux. So even when the circuit is closed, it'll still have 0 electric flux at that specific point in time, which means it can't build up any charges on there, which means the voltage across the capacitor is 0 when we first start. Okay. This has to deal with electric flux. You don't need to know what it is, just know that it's resistant to change the second that you put current into a system. Over time, it will pick it up and it'll grab a charge and grab a charge and grab a charge and create a charge separation here, storing those charges, storing and separating those charges. But initially, it doesn't happen. Okay. So over a long period of time, at some time later, let's say a long time later, the current now in the circuit goes to 0 because the battery becomes, the capacitor becomes fully charged. The voltage of the capacitor is the voltage of the battery, which means the charge on the capacitor is simply the voltage of the battery times capacitance. And the voltage across the resistor is equal to 0. Because ideally what's happening is as you add more charges to the capacitor becomes more charged, almost equaling the voltage from the battery at the end. Does that make sense? So if we take a look at current as a function of time, correct, the capacitor cannot exceed the battery in charge. The reason being is there's only so many electrons for it to store, right? It can only store what the redox reaction is giving it. And since they're in parallel, the voltages have to equal and cancel each other out, right? Parallel but opposite polarity, right? So that's why it goes to 0. So if we graph current as a function of time, we see current starts off at a maximum, which is V over R, and it decays going all the way to 0. And if we did charge as a function of time, starts at 0 as a function of time, starts at 0 and goes up to a maximum. Right? And when that discharges, it goes out. But this is how it looks. So this is the charging of the capacitor. And this is, as it charges, it's removing electrons from the current that's flowing around in the loop. So there's less overall current, hence why the current decays in your system. So if we graph it, I is equal to V over R, e to the negative t all over RC. Okay. And the charge equation, Q, is equal to VC 1 minus e to the negative t all over RC. This is just doing the calculus to get those equations, but you don't need to know how to get those equations from your differential. Right? Because if you think about it, this is all a differential. The voltage is equal to current times resistance for Ohm's law plus the charge over capacitance. So if you think about it, I is dq dt, so this is q prime r plus q 1 over c is equal to some number, some voltage. It's a constant. So you get a differential equation. That's how I used it to find each of these equations for growth and decay for your charge and your capacity and your current within the electric circuit. So current is building up on the capacitor. Charge is building up the capacitor, and charge is being lost from this electric circuit. Okay. The amount of energy that you can store on the capacitor is equal to 1/2 times QV, or it's 1/2 CV squared, or 1/2 Q squared all over C. Any questions? Okay. Let's take a look. The passage that's come up before. Any questions on this, by the way, before we move on? And I'm going to delete because I'm going to share a in-class passage. Since you guys said that you guys want more passages to do. It's going to be 2-paged. Let me know when you guys are ready. What does the R stand for? Oh, R is ready. Cool. Sorry, not hip to the new jargon. I'm old. Not as old as Todd, but pretty old. Okay, so this is a guitar type of passage. I want to zoom in a little bit so you can see and read everything. You're not missing anything. Okay, it's a guitar passage. I'll give you guys 9 minutes to do it. I'll skip to the next page in about 6 minutes. You may begin. think that's enough time for this page. I'm going to move on to the second page. We have 1 minute left. All right, that is time. This is one of our Berkeley Review passages. We've had it in stock and series for a while. We had it in development. I helped write some of the questions. So yeah. Number 1, the answer is A. Number 2, the answer is B. Number 3, the answer is D, like dog. Number 4, the answer is B. Yeah, you're lucky I don't write tests for the AMC. AAMC. Oh. Number 5, the answer is A. And number 6, the answer is C. So this is like a typical AMC passage, though. The passage seems hella whack, right? It's like using something you've never seen before, and it just seems like it's out of the blue, right? Right? But you know all these concepts. So let's take a look. So number 1, junction rule. If you know junction rule, you could do number 1, right? You can see that I2, if we only look at this junction right here, I2 plus I3 equals I1. Let's look at number 1. That makes B wrong, that makes D wrong. Okay? And if we look at it, between A and C, which one makes the most sense? So you can see that I1 is equal to I2 plus I3. And then if you manipulate that junction rule, I1 is equal to I2 plus I3. You can see it again from this junction right here. I can do it in red so it's easier for you guys to see what I'm marking up. This junction here, you can see I2 plus I3 equals I1. And then if we look at the voltage of the volume and the voltage of the amplifier, they need to be they're in the same part of the loop, right? Here and here respectively. So they should have the same signage. The volume and the amplifier will be different in C, which is why C is wrong and why A is correct. Okay? Just looking at circuit analysis for number 1. Does that make sense? I'll let you guys look at it some more. Number 2, right? You guys wanted difficult. This is difficult for sure and out there. Kind of like what the MCAT is going to expose you guys to. Number 2, imagine that we replace the volume resistor in figure 1, R volume, with 2 resistors of resistance R1 and R2. If at a certain moment the voltage across the segment R1 and R2 is 5 volts, they're saying it's 5 volts across the whole section, and the current is 50 milliamps, which of the following could be the value of the resistances? So it's 5 volts across here, and the current going across there is 50 milliamps, or 0.05 amps. So resistance is going to be voltage divided by, so 5 times 10 to the negative 2 amps. So that's going to be 100 ohms, right? So which of these add up to 100 ohms? Not A. B works. Not C. Not D. Does that make sense? For number 2. Number 3. This goes back and draws back, right? Because most passages are going to be multiple concepts. But if you notice, every question is one question, one concept, right? First one was doing junction rule and loop rule. Second one was dealing with voltage and resistance, right? And understanding that multiple resistors in series will be additive. Number 3, we're looking at harmonics, right? What's the period in milliseconds if n is equal to the second oscillation of the A string? Number 3. So we know that N2 or N1 has a fundamental of 110 hertz. That means N2 is going to be twice that, right? It's going to be 220 hertz in your system. So it's going to be 1 over 220. For the period seconds or inverse seconds, right? Because remember, period is equal to 1 over the frequency. Yeah, it's one of those things I taught you guys. So then that'll be 1 over 220. So the closest that comes to that is 4.5 milliseconds. Hello? Sorry. Looks like it got unmuted in Pocket. Number 4. So the guitarist plucks the E string and then, while it's vibrating, turns the knob on the guitar, which increases the value of R tone. Shown below are the harmonics N1, N2, and N3 for the E string before the R tone is turned. Which of the following represents the final wave after the R tone has been adjusted? So we got N1, N2, and N3 respectively. So what do we know about R tone? It says so here. This is a cars. Remember how I told you that every test question or every topic is always there's a cars question in here. This is cars represented. When the guitarist increases R tone by turning the knob, so it's right here, is where we're looking at. The higher frequencies of sounds produced by the guitar are attenuated, resulting in a tone with less treble, or in other words, less amplitude. So we're going to try to decrease all the relative amplitudes of each of these for the higher frequencies. So it doesn't affect the fundamental. The fundamental should still be the same. So that gets rid of A. It should make it less. C is still the same for N2. And D has attenuated N2 so much that it's less than N3. They should be proportional. So the best one is answer choice B. Okay. It's looking at details and reading, right? Higher frequencies attenuated or reduced in amplitude. Number 5, what is the frequency in hertz of this resultant wave? Remember we talked about the thing called beat frequency? One frequency with another close frequency gives us a frequency of the resulting, which is the difference of these two frequencies, giving us what we call our beat frequency. So 165 hertz minus 110 hertz is 55 hertz. And see, all those topics that I've taught you coming back with an electric circuit twist, right? And number 6, the guitarist plucks the A and low E strings together, which have frequencies of 110 and 82 hertz respectively. The oscillating current in the circuit has an amplitude of I0 and dissipates an average power of PEAE through our volume. The guitar stops the vibration of these strings and plucks the A and D strings together, which have frequencies of 110 and 147 hertz. The circuit current still has an amplitude of I naught, but now has an average power of a average AD, and it's dissipated through our volume. So how does AE compare to the power average of AD? Isn't the power just the current? And they told you that current is the same here and here. I naught. And then the volume, the voltage is the voltage across the volume, right? So it's the same R volume, same R volume. So to me, they're the same. I naught and the same R volume. But this is typical to what you're going to see on the MCAT. Now that we went over it, you see how simple and what it is. No worries, Jonathan. I just muted your phone. I'm pretty sure you just did it by accident. But you can see how simple what the simple concepts that we've talked about and how they can present it in a different light. And that's why I want you guys to get exposure to more passages by doing more practice tests, by doing all the questions in our book, and getting yourself ready for these types of questions that they can give to you, right? Because that could have been, instead of a guitar, it could have been some electrical chemical signal, like a circuit that they, inserted into the body that like monitors like cardiac troponin, right? I have a friend that like made a heart sensor that's what they do. And that circuit could be measuring that cardiac troponin. And so then looking at it based on the questions, you can just structure it the same way. Okay. For adjusting like the sensitivity of the sensor and all that stuff, like you would for like a guitar with the volume and the knobs and the tone. So with that said, we're done with electric circuits. If you guys have questions, I'll be here for office hours. Otherwise, I will see you guys on Wednesday. We'll talk about atomic structure and nuclear chemistry.